Welcome to our brief on developments of a personal navigation system. This research is performed by the University of California, Irvine. Let me introduce our research team. My name is Andriy Shkel. I am the PI of this project. I'm leading the efforts on miniaturization. I'm also working with my students on development of algorithms and integrated system for self-contained navigation. We call it deterministic navigation. Two of my colleagues are Dr. Zach Casas and Dr. Salmas Kia. Dr. Casas is leading our efforts on probabilistic self-contained navigation. His expertise is in utilization of signals of opportunity for localization and navigation. Dr. Kia is leading our efforts on cooperative localization. Her expertise is on optimization of multi-agent systems for indoor navigation. This is our main driving force, our graduate students. They are supporting tasks on algorithms, instrumentation, hardware development, design, modeling, and microfabrication. I'm also listing our previous contributors. Taking advantage of this format, some of our graduate students will have an opportunity to present their research. Our objective is to design completely 100% self-contained navigation system. Our technical approach is based on three main pillars: deterministic, probabilistic, and cooperative. By combining these three fundamental principles, we are developing a single futuristic microsystem. We call it ultimate navigation chip. Our deterministic approach is based on an inertial navigational system, but with a twist. We integrate the inertial sensors in the sole of a shoe. We also integrate the measurement of the foot-to-foot distance with ultrasonic transducers. We use barometric and ultrasonic transducers to measure elevation. We also use vector magnetometry to compensate for drift in orientation. The second pillar is a probabilistic navigation. It is exploiting freely available signals of opportunity such as LTE and 5G. The signals are not used for navigation typically. In our framework, we utilize the signals of opportunity for localization. And the final pillar is cooperative localization. It is based on exchange of location information between agents along with assigned confidence about their locations. We show that this is a critical aiding source of localization. This is our concept of a futuristic ultimate navigation chip, or uNavChip. In the core of the uNavChip are sensors for deterministic navigation, which is based on aided inertial navigation, accelerometers, gyroscopes, solid-state clocks, altimeters, magnetometers, and ultrasonic transducers. Probabilistic navigation is done by listening to the cloud of signals of opportunity with on-chip spectrum analyzer. And cooperative localization is done by leveraging communication between sensors nodes using ultra-wideband wireless transceivers. Software layer does sensor fusion and provides the overall authentication layer. The goal is to provide the maximum autonomy, security, and precision of the overall uNavChip. Our objective is to miniaturize the state-of-the-art components and integrate it in a single microsystem of the size of only 10 cubic millimeters. We are exploring in parallel three stages of implementation. On the left is our lab on shoe implementation. In this implementation, we are using the best-in-class commercial components. The purpose is to understand what level of navigation accuracy is possible using our approach and algorithms, regardless of the size of the entire system. In the middle is what we call SugarCube implementation. For this implementation, we use the smallest footprint commercial components and then use our custom integration approaches to miniaturize the overall system. And finally, on the right is our uNavChip implementation. This is where we design, build, and integrate from the ground up small print MEMS high-performance sensors. You can see here our most recent version of the overall system, which is only millimeters on a side. Next, our team will update you on the latest and greatest in our developments. We will start with deterministic, then move to probabilistic and cooperative, and culminate our briefing with a demo demonstrating the power of integrating deterministic, probabilistic, and cooperative in a single experiment. I will now turn to Chika Zhao to talk about our development of the deterministic system.
In this slide, we will discuss the development of the lab-on-shoe platform. The lab-on-chip platform is not a miniaturized system, but a platform for investigating sensor fusion solution to add full-mounted inertial navigation system. Last year, we demonstrated lab-on-chip 1.0. This year, we developed the lab-on-chip 2.0 system, where we removed the backpack and moved all the components, including computational unit, battery, and data transmission module, to the shoes. This change allows us to have more reliability and more degree of freedom when conducting experiments. On top of that, we integrated an additional sensing modality, the ultra-wideband. The ultra-wideband is programmed to communicate with other ultra-wideband on the other shoe or other agent. The sensors on the current version of the system includes IMU, barometer, ultrasonic transducer, and ultra-wideband, compared to the lab-on-chip 1.0. The 2.0 version has a smaller physical size, higher sampling rate, and additional sensing modality. In the next slide, we will show you a miniaturized version of the system. This is the first generation of the miniaturization, SugarCube platform. The two pictures shows a prototype and a compact PCB realization of the system. The physical size of the PCB is 2 by 2 by 0.5 inches. The current version includes an IMU, a magnetometer, a microcontroller, a Bluetooth module, and a battery. We designed customized firmware for the SugarCube platform. The firmware on the microcontroller includes two modules, sensor acquisition and navigation solution. Sensor measurements collected from sensor acquisition module are input to the navigation solution module. And the navigation solution module produces current location of the user using a zero velocity update aided inertial navigation system. The estimated position are sent to a remote display via Bluetooth for visualizing real-time position of the user. In the next slide, we show a video of the SugarCube.
In this video, we demonstrate a prototype of the SugarCube navigation platform. The SugarCube includes an IMU, magnetometer, microcontroller, battery module, and Bluetooth. The microcontroller provides the position of the user in real time based on zero velocity update aided inertial navigation system. This information is sent to a remote display through the Bluetooth module. The remote display shows the user's coordinate in local and global frames with the satellite map. The pedestrian in this video walked a closed-loop trajectory on different terrains, including flat plane, slopes, and stairs. We assumed GPS signals are available at the initial position, and the onboard magnetometer calculated the initial heading once the system is powered. The total duration was 1 minute and 10 seconds. The accumulated displacement error at the end of the demonstration was 0.9 meters.
Good morning, good afternoon, or good evening, everyone. I'm Zach Cassis, a co-PI on the project, and my team has been responsible for the probabilistic part of the ultimate navigation chip. And what we are trying to do is to resolve the challenge that emergency responders indoors cannot use GPS or more generally GNSS signals to localize themselves and navigate. And our approach to do this is to use what we call probabilistic navigation with signals of opportunity. Now, these signals are not intended as navigation sources, and they include cellular, AM/FM radio, digital television, Wi-Fi, or signals from other satellites, like example, low Earth orbit satellites. And what we are trying to do is to use them to navigate and turn them into something similar to a GPS signal. So our previous analysis showed that the biggest bang for the buck is to use cellular long-term evolution or LTE signals of opportunity to navigate. And the reason for this is that these signals are very powerful indoors. In fact, we've showed in previous NIST presentations that those signals are 20 to 30 dBs higher and received power than GPS outdoors. So they are very powerful. They are really getting transmitted from our backyard, so to speak, unlike GPS signals that are coming to us from space. Two, they are abundant. We have dozens of towers around us, cellular towers around us, and that the number is supposed to increase dramatically with 5G. They are geometrically diverse, which helps us localize ourselves in a more accurate fashion. And they have a large bandwidth, which helps us in mitigating an issue that I will talk about shortly, which is multipath. And finally, we all like free things. So they are technically 100% free. We can, if we know how to use them cleverly, the way I will show you soon, you can use them for free. You don't have to be a subscriber to that particular network. And in our experiments, we've used signals from different providers, AT&T, Verizon, and others. So let me show you some of our latest results with those signals. So last year, we were dealing with one of the challenges that I mentioned earlier, which is the multipath in these signals. So what multipath causes is it ambiguates the line of sight, which helps us know our range from the transmitter to the receiver, and introduces an error due to that. So what we are trying to do is to beamform towards the line of sight component and null the non-line of sight component, or null that multipath. So why is multipath dangerous? If you see here, the green is the true range. The red is the ambiguated range due to multipath. And then the blue is what we can recover if we can null the multipath components and beamform towards the non-multipath component. To do this, we can use a physical antenna array, but this is not practical for our application. So what we are going to do, we are going to synthesize an antenna array using techniques that I will show shortly. So this is the overall block diagram of our framework. So we have an LTE receiver, an extended Kalman filter, and a beamformer. And I've shown this last year, but what we've done this year is we replaced the spatial smoothing block and the Esperit block, which helps us mitigate multipath, with a machine learning approach, a deep neural network approach to basically help us with these blocks. So this experiment is something we had done in the past. You had probably recall it if you've watched the presentation. We've navigated in the University of California, Riverside, in an indoor environment. This is the experimental setup, the hardware and software we've used. A USRP, we have several antennas simply to listen to different frequencies transmitted by different providers. The green in the bottom right block or window is the true trajectory that we are traversing. The blue is what I showed last year. This is the LTE synthetic aperture navigation solution. And the red is what we are able to achieve in our work over the past few months, which is replacing the synthetic aperture with a machine learning approach or a deep neural network approach. And as you can see, it improved our performance. So let me show you how it improved it. If you look here in this row, this is what I showed last year. The root mean squared error along the trajectory, which was about 109 meters, was 4 meters. And we brought this down to just 1.73 meters. We also improved significantly in the standard deviation, and even we reduced the maximum error from about 11.5 meters to about 9.5 meters. We also reran the results that we achieved last year, which were conducted in the Engineering Gateway building in the University of California, Irvine. This row here is the previous results from last year with the LTE synthetic aperture navigation approach. So 3.93 meters, 1.65 meters, 5.63 meters for the maximum error, and they all improved upon incorporating the deep neural network. And I have to stress here that all what we are using is the signal. We are not fusing it with any sensor. We are not adding an IMU or a ZAPT or an ultra wideband or a collaborative or anything. This is simply a state-of-the-art receiver that we have designed, along with sophisticated signal processing techniques for mitigating multipath via beamforming and a machine learning approach. Now, probably what's on your mind is 5G. When we started this project, 5G was not into the picture, and now 5G is what's on everyone's mind. So we've conducted a quick study to assess how our existing framework would function when we move it to 5G. 5G is not too different from LTE, unlike previous generations. So this is a quick study to show different E node Bs and different G node Bs. Those are LTE and 5G signals coming into engineering gateway. So what you are seeing here is a different floors, different corridors in the environment, different hallways where we collected signals to see and compare the LTE signals we are receiving with the 5G signals we are receiving. And those, this is the hardware setup. And finally, those are the results. So you can barely see noticeable differences for the carrier to noise ratio in different floors, different environments, including a bridge that connects the two buildings, including the elevator, and so on and so forth between LTE and 5G. In fact, some of the key takeaways that I want to leave you with are that the carrier to noise ratio was consistent at different locations between 4G and 5G. And there is really no clear pattern in the carrier to noise ratio behavior in different floors, which actually is good for our purpose. And we would expect a consistent navigation performance throughout the entire building. The signals, surprisingly, were powerful inside the elevator, and we were going up and down, and we noticed surprisingly good powerful behavior even inside the elevator. So with that, I will leave you to the next part of the ultimate navigation chip, and thank you for your interest in our work.
Next, I am going to go over cooperative localization component of our work. My name is Solmaz Kia, and I am one of the co-PIs of this project. So for a group of firefighters, the idea in cooperative localization is to use relative range measurements between team members to generate an infrastructure-free aiding signal to improve the localization accuracy of foot-mounted inertial navigation localizers. In the scenarios that the firefighters work in, the accuracy of local estimates of the agents can vary depending on how long they have been in the field. Maybe some of the agents had a better access to signals of opportunity or even GPS and improved their localization accuracy. Then cooperative localization allows agents with higher uncertainty to reduce their localization error by taking relative range measurements from agents with higher accuracy. The cooperative localization filter that we have designed acts as an augmentation service on top of the local positioning filter of the agents and becomes active only when the agent takes a relative measurement from another agent. In this setting, agents need to communicate only at the time that cooperative localization is active. To enable non-line of sight interagent ranging and infrastructure-free interagent communication, we have chosen ultra-wideband technology for both ranging and communication. In this project, we are working with DWM-1000 ultra-wideband transceivers. To enable efficient multi-agent communication, we have designed a novel dynamic TDMA MAC protocol for ultra-wideband communication. We have also augmented our dynamic TDMA protocol with a data-driven communication protocol to schedule cooperative localization updates selectively to reduce the communication cost while maintaining an acceptable level of localization performance. Our experimental studies by 6 agents shows a packet loss of well under 6%. The data-driven protocol also reduces the communication incidences between the agents by an order of magnitude with only a marginal loss in localization performance. The challenge with ultra-wideband ranging is how to account for ranging biases, especially in non-line of sight measurements. Unlike the common approaches that try to identify and discard non-line of sight measurements, we have designed a novel real-time bias compensation for cooperative localization with non-line of sight interagent ranging. Another innovation in our work is to use probabilistic framework for non-line of sight identification and design our cooperative localization accordingly. To demonstrate our results, here is an experimental study with 3 pedestrian agents to emulate opportunistic improvement with help of external aiding. We have included 2 beacons in our test as well. Agent 2 and Agent 3 start walking from the same location but in opposite direction. Agent 1 waits along the Agent 3's path and joins the operation when Agent 3 gets closer. The experiment stops when Agent 2 and Agent 3 return back to their start point, so we could use their loop closure error as our performance indicator. The power-based modal discriminator was used to identify each measurement's mode probability. We ran several parallel localization filters on each agent. For all 3 agents, the INS-only localization using the foot-mounted IMU due to error accumulation results in trajectories that drift. Due to obstructions between agents such as bushes, tree, wall, swimming pool equipment, and people, the ultra-wideband interagent ranging measurements are under a mix of line of sight and non-line of sight condition. The filter that ignores the bias in the measurement results in poor localization accuracy and even filter divergence as part of the trajectory. On the other hand, our proposed algorithm, called here AUCL algorithm, by employing bias compensation and taking into account the probabilistic nature of the power-based ultra-wideband modal discriminators, delivers the best localization and the smallest loop closure error of about 1% of the travel distance of the trajectory, which is of order 240 meters. As expected, a filter that uses deterministic modal identification to exclude the non-line of sight measurements, or the filter that processes ultra-wideband measurements in an unimodal form, results in an inferior performance compared to the AUCL algorithm that we proposed. Lastly, the plot in green with legend AUCL2 agents for Agent 2 and Agent 3 shows the performance of the AUCL algorithm for these 2 agents when measurements with respect to Agent 1 were discarded. Since Agent 1 started late, it had a higher localization accuracy. Excluding measurements with respect to Agent 1, as the green plot shows, results in loss of performance for Agent 2 and Agent 3.
In this part of the presentation, we will demonstrate an integrated system that merges deterministic, probabilistic, and cooperative approaches. The block diagram shown here illustrates the integrated framework. We used an extended common filter to fuse navigation observables from the 3 approaches and estimate navigation results. The core of the integrated system is the deterministic block of the framework, which uses zero-velocity update-aided inertial navigation system enhanced by a foot-to-foot ranging and a barometer. When UWB communication between multiple agents are established, the system is augmented by inter-agent ranging management. The probabilistic approach is used to bound position error growth when opportunistic cellular LTE pseudo ranges become available, which extends the usage of the integrated system for long navigation period. The experimental setup of the integrated system is presented in the next slide. This is our demonstration setup. The pedestrian was the lap-on-shoe 2.0 platform to acquire measurements of IMU, altimeters, ultrasonic sensors, and UWB. The UWB on the right shoe is used for 2 purposes. First, it's connected with the UWB on the left shoe for foot-to-foot ranging. Second, it communicates with the UWB mounted on other agents for inter-agent range measurement. The pedestrian carries the probabilistic setup on his back. The setup consists of a quad-channel National Instrument Universal Software Radio Peripheral 2955, a laptop, a lithium battery, and a storage unit, all packaged in the backpack, on which 4 omnidirectional cellular antennas are mounted. In the next slide, we show the demonstration video.
To evaluate the proposed integrated system, a similar scenario of a previous experiment was conducted at the Engineering Gateway building located at the University of California, Irvine. Initially, the agent was assumed to have a prior information about its position as the agent entered from outside and had access to GNSS signals. The video is showing a rendering of the traverse trajectory in a 3D map of the building, which was obtained using LiDAR and camera from a smartphone device. The bottom right window shows a video of the agent walking in the building while performing the experiment. The bottom left window shows the received LTE signal's carrier to noise ratio corresponding to 4 nearby LTE towers, or what is known as E-node Bs. The time history of the navigation solution produced via the proposed approach is demonstrated in red, while the green dot shows the current position. As the agent established communication with another agent, represented in yellow here, interranging UWB-based measurements were performed. As you can see, this experiment includes terrain of flat surfaces, slopes, stairs, and later an elevator. As the agent approaches another agent, the UWB-based relative measurements between the agents are exploited too. In the entire experiment, the agent traversed a distance of 600 meters in 14 minutes. The standalone deterministic approach maintains small position errors over the duration of the experiment. However, the probabilistic component is expected to expand this accuracy for longer navigation periods. Here, you can see the navigation solutions of different frameworks, along with the positioning accuracy metrics summarized in the bottom right table. The ground truth was found using a combination of manually determined checkpoints in the building and the post-processing of the recorded video while the agent was performing the experiment. The integrated solution achieved a two-dimensional 2D positional root mean square error, RMSE for short, and a final error of around 1 meter and 80 centimeters respectively, and a 3D position RMSE and final error of around 1.4 and 1.1 meter respectively.
To conclude this briefing, we are investigating a very exciting technology. This is the futuristic ultimate navigation chip. We are trying to take a glimpse of the future and imagine what the technology of navigation and localization may look like in not so distant future. Our vision is to create a single chip, size of an apple seed, a device combining on a single chip the deterministic, probabilistic, and cooperative functions. We believe these three functions are critical for success. In parallel, we are developing three different platforms: lab-on-shoe, SugarCube, and uNavChip. Each platform has its own purpose and provides us with the flexibility for parallel development of algorithms, packaging, microfabrication, and field testing. Today, we demonstrated the feasibility of our approach. We have demonstrated the capability to obtain the localization accuracy on the level of 1 meter after 14 minutes of navigation with only deterministic approach. We also demonstrated that LTE can provide 1.5 meters of accuracy. This suggests that with the availability of the LTE signals, we can significantly extend the duration to hours of operation. In this short briefing, we showed that our recent results and provided evidences of the developed capabilities. And finally, we would like to acknowledge NIST and the PSCR program for the financial assistance. We would also like to acknowledge Joseph Grasso for his leadership and guidance as a program manager. This completes our briefing. Thank you.